Hello, today we're going to discuss the topic of automatic formal systems. Formal systems can be automated, and then an automatic formal system performs steps on their own without having to be moved. And so a computer then is an automatic formal system. It is a formal system, but also an automatic formal system. Likewise, if the brain instantiates a formal system, then it is an automated formal system since it needs no outside players. And so an automatic formal system is going to be a physical device with the following characteristics. First, that some of its parts or states are identified as the tokens of some formal system and in a particular position. And second, then in its normal operation, it automatically manipulates these tokens according to the rules of that system. It respects the rules of that system. In order for us to have automation, we need finite playability. Again, here the notion of algorithm is invoked. So no infinite or magical powers are required to play. Hence, we have what Haugeland calls the automation principle. It says that whenever the legal moves of a formal system are fully determined by algorithms, then that system can be automated. So, an automatic formal system in Haugeland's sense is automated in virtue of its implementing an algorithm, that is, an effective, finite, purely mechanical procedure. Now, formal equivalence was all that was required to deal with formal systems. But automatic formal systems may demand something more. And this is dynamical equivalence. If you're going to model automatic formal systems, we might require dynamical equivalence. And so systems which are formally equivalent and which make equivalent choices in each position are dynamically equivalent. Take the example of a Turing machine, which is the theoretical ancestor, as you know, of all our digital computers. If you remember, anything that can be done by an effective method can be done by a Turing machine, and vice versa. And so one automatic system can formally implement another one by imitating it. And so if you have that, then some of the configurations of tokens or positions of the former can be seen as the tokens or positions of the latter. And as the former follows its own rules, it automatically manipulates those tokens of the latter in accord with the latter's rules. And so we have the notion of formal equivalence with the added element of choice. So again, now in terms of the Turing machines, so any automatic formal system can be formally imitated by some Turing machine. And what Turing proved is that there are special Turing machines called universal Turing machines, which can be programmed to imitate any other Turing machine. And now we can restate the Church-Turing thesis, which any effective or mechanical method can be carried out by the universal Turing machine. And so we can also express it in different ways. For instance, any mechanical computation can be performed by a Turing machine, or that we can model any formal system with a Turing machine, or that algorithm is anything equivalent to a Turing machine, or that every algorithm can be expressed in a language for a Turing machine. All those say more or less the same. So if we combine the Church-Turing thesis and Turing's theorem, a universal Turing machine can imitate any automatic formal system whatsoever. Now, there's a problem there if you're going to have an automatic formal system, which is that at each step, the system must decide on a move. However, in some systems, the number of available legal moves can be huge. Example, chess. The number of possible chess games is just astronomical. It boggles the mind. So we have these systems that are non-deterministic as opposed to a deterministic system, Turing machine. At every step, there's only one step that follows. And so the problem is how to choose the best move. Well, there's no algorithm necessarily for that because you have a combinatorial explosion, as I said. The number of possible moves grows at a breathtaking pace. So we need to implement a heuristic. A heuristic, in comparison with an algorithm, is a rule of procedure that is reliable but not infallible, whereas an algorithm is guaranteed to give you a result in a finite number of steps. So far, then, we have, again, the notion of formal system and the notion of formal systems that are token manipulation systems, and the digital nature of formal system that allows for physically different systems to be formally equivalent, and this entails the property of medium independence. And then we also add the property of automaticity or automation, and that entails automatic rule application. But automation requires algorithm. And so we have the notion of formal imitation and the requirement of dynamical equivalence as opposed to mere formal equivalence. And so we can form a new question for the computationalism, a new requirement. Is the brain, at some abstract level, dynamically equivalent to a digital computer? Notice that dynamical equivalence entails formal equivalence, but not the other way around. Thus, our previous standing question, is the brain at some abstract level formally equivalent to a digital computer, is subsumed under the new one. And so we have then under this conception that digital computers would be automatic formal systems. And the characteristics then is that, just to repeat, that a formal system, the automatic formal system is a formal system, is a token manipulation system, which is a digital system that is medium independent. We have the characteristics of formality, the characteristics that is automatic, and also the characteristic that it is interpreted. But we haven't said anything about that. Well, stick around and then we'll talk about that in our next video. Well, cheers.